So right now, algorithms are managing, trillions of dollars in the stock market.
Yeah, trillions.
And then they're mathematically brilliant, right? Hyper accurate. But according to this groundbreaking April 2026 paper we're looking at today, they're actually completely blind to what you, the investor, actually want them to do.
Yeah, it's honestly a massive blind spot in quantitative finance. I mean, we've built these incredibly sophisticated AI systems to predict where the market is going, but they operate in a total vacuum.
Right.
They don't know if the money they're managing belongs to like a 25-year-old day trader with a massive appetite for risk or, a 75-year-old retiree who just desperately needs to preserve their capital.
And that is exactly our mission for this deep dive today. Okay, let's unpack this. We're looking at a paper titled Machine Learning Meets Markowitz.
Great paper.
Yeah, authored by researchers from Tongji University, Tsinghua University, Duke, and NJIT. And basically, they diagnosed this fundamental structural flaw in how Wall Street uses AI, and then they built this revolutionary new framework to fix it.
Right. We're essentially moving from AI that just, merely predicts the stock price to an AI that actually understands the constraints and desires of the user.
Which is huge. But to understand the cure, we first kind of have to look at the disease, right?
Absolutely.
Yeah.
The paper calls the current standard in the industry the predict then optimize approach. And honestly, the problem is built right into the name.
Predict, then optimize.
Exactly. It completely separates the process into two entirely disconnected steps.
It's kind of like a two-step dance, but the partners are, I don't know, in completely different rooms wearing noise-canceling headphones.
That's a really good way to put it.
So step one is pure prediction. The AI uses these statistical models to look at all the data and predict future asset returns.
Right.
And it evaluates its own success by minimizing something called mean squared error, or MSE, which basically it looks at the entire universe of stocks and tries to get its average prediction error as close to zero as possible across the board.
Yeah, and then comes step two. You take that giant list of predictions, you hand it over to a mathematical optimizer, plug in the specific human investor's risk preferences, and the optimizer just spits out a portfolio.
Okay.
But the researchers point out that creating this firewall, this separation between the prediction engine and the optimization engine, is deeply problematic.
I do want to push back on that just a little bit, though.
Sure.
Why is that problematic? I mean, if I want a good portfolio, shouldn't I want the most accurate predictions possible across the entire market?
It seems totally logical, right?
Yeah, like it just seems logical that you'd want the AI to, ace the global math test before you ask it to buy anything.
It does seem logical, until you realize that in the real world of investing, not all forecast errors are created equal.
What do you mean?
Well, in step one, the AI is trained to treat every single stock as equally important. It evaluates its own performance by looking at its average accuracy everywhere. But it has absolutely no idea who it's predicting for. The algorithm doesn't know if the end user is a high-flying, aggressive hedge fund or, like we said, a highly conservative teacher's pension fund.
So it's optimizing for an average investor who doesn't actually exist?
Precisely. And the paper uses this brilliant four-asset example to illustrate why this breaks down so badly.
Oh, yeah, the miniature stock market?
Right. Imagine a market with just 4 companies. 2 of them are large-cap, incredibly stable firms.
Like utility companies or established consumer goods?
Exactly, driven by steady earnings yield. And the other 2 are small-cap, highly volatile tech startups driven purely by growth factors.
Okay, so a pretty standard market dynamic. You've got your slow and steady stalwarts and your high-risk, high-reward wildcards.
Now, if you train a traditional AI using mean squared error, its goal is to find the mathematical middle ground.
Right, it wants the lowest average error.
Right, so it minimizes its prediction errors globally across all 4 stocks, kind of compromising here and there to get the lowest possible overall MSE. But imagine you are managing that conservative pension fund. Your mandate is capital preservation.
I cannot lose money.
Exactly. You are never, under any circumstances, going to buy those volatile, small-cap tech stocks. You only want the safe, large-cap ones.
Which means, wait, so the AI just burned a massive amount of computing power and compromised the accuracy of its large-cap predictions just to try and accurately predict the price of small-cap stocks that I am legally not allowed to buy anyway?
That is the fatal flaw, yes.
Wow.
The researchers demonstrated that if you take an artificially skewed model like one that intentionally ignores the small-cap stocks and heavily overweighs the factors driving the large-cap stocks, that skewed model actually performs much worse globally.
Wait, really?
Yeah, its overall statistical error goes way up.
Because it's failing the global math test on purpose.
Right. But for our conservative pension fund investor, that failing model generates significantly better realized utility.
Because it's focused.
Exactly. It makes them more money, safely, because it is hyper-precise on the specific assets they actually intend to put in their portfolio.
That makes so much sense.
The traditional statistical objective, minimizing the average error across everything, is fundamentally misaligned with the decision-oriented goal.
Right.
The goal isn't perfect global prediction. The goal is building the best possible portfolio for a specific human being's needs.
So it's kind of like training a financial AI based purely on mean squared error is like a tailor making a suit by measuring the average body size of everyone in the entire city.
Oh, I love that.
Rather than just measuring the specific person standing in the shop waiting to buy the suit.
That is a perfect visualization.
Yeah.
A one-size-fits-all set of return forecasts inevitably leads to suboptimal portfolios.
Yeah.
You just have to integrate the specific constraints and goals of the end user into the prediction process itself.
Which brings us to the logical cure. If separating the prediction step and the optimization step is the disease, you just, smash them together.
You fuse them.
Yeah.
Yeah.
But knowing Wall Street's obsession with optimization, I just have to assume people have thought of this before, right? Why are we only seeing this paper in 2026?
Because mathematically, fusing those two steps is incredibly difficult. And this is the core technical breakthrough of the paper.
Okay.
The researchers propose an end-to-end learning framework, or E2E. They abandon the predict and optimize routine entirely.
Right.
Instead, they integrate the portfolio construction process directly into the neural network's training stage.
Meaning the AI changes how it evaluates itself during training?
Exactly.
So instead of looking at its output and asking, did I predict the exact price of all 4 stocks correctly, it runs a simulation and asks, if I used my predictions to actually buy a portfolio for the specific conservative investor, how much money did that specific portfolio make under their specific rules?
Spot on. The model evaluates its own predictions by the realized utility of the resulting portfolio.
Okay, so where's the math problem?
Well, the hurdle here involves a concept in machine learning called backpropagation. When you train a neural network, you feed it data, it makes a guess, you calculate how wrong the guess was, and then you send a mathematical signal backward through the network to adjust the internal weights so it does better next time.
You have to be able to trace the error back to its source.
Yes, and that backward signal requires smooth, differentiable math. It needs slopes and curves to slide down to find the optimal answer.
Okay.
But a portfolio optimizer isn't smooth. It is full of hard constraints. Things like no short selling or do not allocate more than 10% of capital to any single sector.
Right, those are binary rules.
Exactly. They're hard walls.
Yeah.
Mathematically, they're inequalities. When the backward-flowing learning signal hits a hard constraint, it just shatters. You cannot calculate a gradient through a hard wall.
Here's where it gets really interesting. Because it sounds like trying to train someone to navigate a maze while blindfolded, right?
Okay, yeah.
You give them a walkie-talkie and you guide them based on their mistakes. But
Right.
every time they hit a dead end, a hard constraint, the walkie-talkie completely cuts out.
Oh, that's a great analogy.
So they know they failed and hit a wall, but they can't learn why they hit it or how far they need to adjust their previous steps to avoid it next time. So how did the researchers fix the walkie-talkie?
They utilize something called Karush-Kuhn-Tucker, or KKT optimality conditions.
Okay, sounds complicated.
Well, without drowning us in calculus, they basically found a way to turn the convex optimization problem, the classic Markowitz optimizer with all those hard rules, into a transparent, differentiable layer within the neural network.
How does that actually work in the maze, though?
Think of KKT conditions as putting a mathematical GPS tracker on those maze walls.
Okay.
The AI still cannot walk through the wall. The rule of no short selling remains absolute. But when the backpropagation signal hits that barrier, instead of cutting out, the KKT math translates that hard wall into a smooth penalty gradient.
Oh, I see.
It sends a signal back saying, you hit the wall, and here is exactly the angle and slope you need to adjust your internal weights by to slide past it on the next attempt.
Wow.
The backward learning signal can now flow right through the optimizer and update the prediction engine based on the final portfolio rules.
Wait. So instead of just grading the AI on a theoretical math quiz, You are dropping it into a simulated market, forcing it to trade under the investor's specific rules. And because of this KKT math, the AI can trace exactly which of its initial data interpretations caused it to lose money at the very end of the process.
That is the massive shift.
Yeah.
Yes. By calculating gradients through a constrained optimization problem, the AI actually learns which specific market signals matter most for the end goal.
That's incredible.
It stops caring about predicting the whole market perfectly and starts obsessing over finding the exact signals that build the best allowable portfolio.
Okay, the mathematical theory is elegant. I'll give them that. But look, a math trick is great in a vacuum. The real stock market is brutal.
Oh, yeah. Very messy.
It's messy, full of friction. So how does this end-to-end model actually perform when it's thrown into the deep end with real money on the line?
Well, the researchers didn't hold back on their testing. They used a massive, granular data set from China's A-share market, spanning from 2010 to 2023.
That's a lot of data.
We were talking about 5,489 stocks, 415 different firm characteristics, and roughly 6 million stock day observations.
Why the Chinese market specifically, though?
Because it has incredibly strict short-selling constraints. It is notoriously difficult and often outright impossible to short a stock in the Chinese A-share market.
Oh, right. So it's a great test for constraints.
Exactly. It makes it the perfect laboratory to test how AI handles real-world constraints.
Yeah.
When they ran the traditional MSE model, the one that just predicts prices and ignores constraints until the end, it looks spectacular on paper,
How spectacular.
generating Sharpe ratios exceeding 9.0.
Wait, 9.0.
Um,
For context, for you listening, a Sharpe ratio just measures how much return you get for the risk you're taking. A Sharpe ratio of 1 is solid, a 2 is fantastic.
Yeah.
A Sharpe ratio of 9 is basically a legally allowed money printer. Like, it's unreal.
It is unreal, literally. The paper reveals that almost all of that alpha, that incredible outperformance, was concentrated in the short leg of the portfolio.
Oh, I see.
The traditional AI was brilliantly identifying stocks that were about to collapse.
Oh.
But in the real world, in China, you cannot act on that information.
Because you can't short them.
Exactly. So a Sharpe ratio of 9 is just a mirage.
So what happened when they forced the models to play by the actual rules, imposing a strict long-only constraint?
The end-to-end framework absolutely blew the traditional MSE model out of the water.
Really?
Yeah. Using a specific three-layer neural network architecture they call NN3, the traditional MSE model managed a 40.0% annualized return.
Okay, not bad.
But the E2E model, which was trained while feeling the wall of that long-only constraint, achieved a 43.6% annualized return.
Hold on, I need to be skeptical here for a second. 43.6% annualized returns.
I know it sounds high.
In an AI simulation. I mean, anyone can overfit an AI model to look like a genius in hindsight by torturing the historical data.
Fair point.
How do we know this isn't just data mining? Machine learning models are notorious for finding, like, tiny, fleeting advantages, rapidly swapping the portfolio around every day, and just bleeding the investor dry in broker fees, bid-ask spreads, and taxes?
You're exactly right, and that is the Achilles heel of quantitative finance. But the paper tackles transaction costs head on.
Oh, they do?
Yeah, they tested the models against transaction cost rates, or TCRs, ranging from 0 up to 40 basis points per trade.
Okay, but couldn't the traditional model just add a simple rule at the very end of its process? Just tell the optimizer, hey, don't trade too much, it costs too much money.
That is the industry standard Band-Aid, basically. And the researchers tested that exact setup, calling it MSE-Opt.
MSE-Opt, okay.
It uses the traditional prediction engine, but adds a post-prediction penalty on trading volume.
And how did it do?
At 30 and 40 basis points of transaction costs, the raw traditional model's returns actually turned negative. It literally traded itself into a hole.
Wow.
The MSE-Opt approach, the one with the Band-Aid, did survive. It forcibly reduced the portfolio turnover to stay profitable.
Makes sense.
But the end-to-end model did something entirely different, something the traditional model physically cannot do. E2E lowered the signal turnover.
Signal turnover. Wait, as in the AI actually changed what kind of data it was looking for?
Exactly. Because E2E is cost-aware during its actual training phase, it experiences the simulated bleed of those transaction fees.
It feels the pain early.
Right. It systematically rewires its own brain to ignore high turnover signals. Imagine a pattern like a short-term reversal. A stock dips sharply, and the data suggests it will bounce back up tomorrow.
In a frictionless vacuum, that's infinite money.
Right. But in reality, exploiting that requires buying today and selling tomorrow. The broker takes a cut, the spread takes a cut.
So the E2E model sees that.
Yeah, the E2E model sees that pattern, simulates the trade, feels the pain of the fees, and says, I see the short-term signal, but it is too expensive to execute. I'm going to assign it a lower weight.
That's crazy.
It systematically favors lower-cost, longer-term fundamental factors. The traditional model can't do that. It just blindly screams BUY at every short-term blip, and the optimizer at the very end just has to frantically ignore those screaming predictions to save on fees.
So the E2E AI is actually learning patience.
Yes.
It's developing a long-term investment philosophy because it feels the mathematical friction of trading. That is wild.
It really is.
Okay, so it survives strict market rules like short-selling bans, and it survives the brutal friction of transaction costs. But the final test isn't market mechanics, right? It's human psychology.
Oh, absolutely.
How does it handle fear?
The human element is the ultimate variable. The researchers wanted to see how well E2E adapts to different levels of risk tolerance, from aggressive to highly conservative.
Okay.
So they compared E2E against the traditional MSE approach, and they also introduced a third framework called parametric portfolio policy, or PPP.
PPP, parametric portfolio policy, is interesting because it's almost a completely different philosophy, isn't it?
Very different.
It skips the whole expected return step entirely. It basically takes raw firm characteristics like a company's size or its price-to-earnings ratio and uses a neural network to map that data directly to portfolio weights.
Exactly.
It draws a straight line from raw data to buying action.
PPP is incredibly direct. It is decision-aware, but it lacks a formal, rigorous mathematical optimization layer like Markowitz. It just relies on the neural network to figure out the mapping.
And how did it compare?
The paper found a very telling crossover point. For highly risk-tolerant investors, like aggressive hedge funds that just want maximum returns and don't care about massive price swings, PPP actually beats the traditional MSE approach.
Oh, interesting.
Because PPP is focused entirely on the end goal of maximizing that aggressive utility function, it is highly successful at chasing high returns.
But I'm guessing that straight line from data to action breaks down when the investor gets scared.
You'd be right.
Like, if I'm managing a teacher's pension fund and my #1 goal is minimizing variance and avoiding a market crash, why doesn't PPP work for me?
PPP completely falls apart for conservative investors, and it loses to the traditional MSE model in those scenarios.
Why is that?
Because PPP lacks an explicit optimization layer to strictly control variance. When your primary mandate is minimize risk at all costs, a neural network's fuzzy, direct mapping from data to portfolio weights just isn't tight enough.
It needs boundaries.
Right. It doesn't have the rigorous mathematical safety checks. The explicit Markowitz optimizer used in the traditional MSE approach clamps down on variance much more effectively.
Okay, this paints a really clear picture of the landscape then. We have the traditional MSE model, which is good at being safe because it uses a strict optimizer, but it's bad at chasing returns because its predictions are disconnected from the user's goals.
Exactly.
Then we have PPP, which is great at chasing returns because it directly maps to the goal, but terrible at being safe because it lacks a mathematical safety net.
Which leaves the end-to-end framework.
Right.
E2E takes an explicit optimization layer and embeds it entirely inside a decision-aware neural network.
Yeah.
It truly is the best of both worlds. The data shows that E2E dominates both benchmarks across the entire risk spectrum. It generates a vastly superior, efficient frontier.
So what does this all mean? It's kind of the first true chameleon AI in finance.
That's a great word for it, chameleon.
You just tweak the utility dial, the human preference input, before you start training, and it morphs. Dial up the risk tolerance, and it acts like a ruthless return chaser. Dial up the risk aversion, and it becomes a strict, paranoid risk manager.
And we connect this to the bigger picture. It proves that investor heterogeneity, the simple fact that different humans have different goals, is no longer an afterthought bolted onto the end of an algorithm.
Right.
In traditional finance, you predict the market and then you deal with the humans.
Yeah.
In this E2E framework, the human is an endogenous component of the learning process.
From the very beginning.
Yes. An aggressive hedge fund and a conservative pension fund will feed the exact same market data into this E2E model, and the model will generate completely different internal valuations of that exact same data.
Because it learned during training that a stock, which is good for the hedge fund, is mathematically bad for the pension fund, regardless of whether the price goes up.
Exactly. It redefines what accuracy means in machine learning.
Mm-hmm.
Accuracy is no longer, did I guess the price correctly? Accuracy is, did I fulfill the specific mandate of the human who deployed me?
That is a profound shift in perspective.
Hmm.
And, if you are listening to this and you're managing an institutional fund or building a trading algorithm or even just trying to understand where AI is heading in the broader economy, the lesson here is clear.
Absolutely.
We are moving past the era of the one-size-fits-all oracle. AI is moving from raw statistical prediction to goal-oriented execution. And AI's power is no longer just in its processing speed. It is in its alignment with your specific constraints, your frictions, and your personal preferences.
And, the researchers actually touch on this in their conclusion when they discuss unexplored applications for this framework.
Oh, yeah. What else can it do?
They point out that E2E is so flexible, it could easily be trained to factor in the highly specific tax profile of an individual investor for complex tax loss harvesting.
Oh, wow.
Or it could be used for a pension fund's joint asset liability optimization, where the AI isn't just trading stocks, but simultaneously optimizing against the complex schedule of payouts the fund owes to its pensioners over the next 30 years.
So it's factoring in complex future liabilities while making micro decisions today.
Exactly. And I want
Yeah.
you to consider the broader implications of that for a second.
Okay.
If we can now train complex neural networks to not just blindly predict the world, but to actively optimize around multi-layered future liabilities in the financial sector, how long until we have personal AI assistants that do the same for our personal lives?
Oh, that's deep.
Imagine an AI that doesn't just predict traffic patterns or suggest calendar events, but actively optimizes your daily decisions against your own personal liabilities, your stress thresholds, your family commitments, and your long-term life goals.
A completely bespoke intelligence trained inside the optimization layer of your own life constraints. That is an incredible thought to end on. We started by looking at algorithms that were completely blind to what we actually wanted them to do, and we finished with a framework that proves AI is at its most powerful when it is built around human needs. Thank you for joining us on this deep dive. Keep questioning the data, keep looking for the why behind the algorithms, and we will see you next time.